last class, we did some data exploration where I taught you different types of exploration. I said we have statistical exploration and we have visualization. We said statistical exploration is a type of exploration that has to do with you getting insight from your data. However, you don't use pictures. What you usually use is you use statistical tools like shape, info, correlation. All these are ways to visualize your data. I'm coming. Okay. While that was the first type of data exploration we did. The subsequent data exploration we did was strictly on data visualization. And we said this type of exploration focuses on using pictures to represent your data. And last week I taught us basically we have top three. It's not that we have only three, we have more than three, but the top three um, tools we use for visualization in Python programming, I said they are Matplotlib, Seaborn, and Plotly. Matplotlib, Seaborn, and Plotly. And we used them last week to perform some visualizations where we visualized some data components and I gave assignments. Although I haven't seen anyone who turned in that particular assignment, I don't know whether you were scared of using the tool or maybe some of you probably must have forgotten. But I gave assignments on performing visualizations using. I was specific. I said you should use a Plotly. Sorry, the file is still loading up. I want it to finish loading. So those were the things we looked at in our last class. And then I also taught you how to do data pre-processing. I said one important data pre-processing you always do is converting any data that is not numerical to numeric. That is if the data is a categorical data. But if the data is not categorical, you are to remove it. For instance, I said data like somebody's name, uh, his first name, his second name, his email, his ID number, all these type of data, you don't need them when you are trying to build a machine learning model. So they are not important. Although they can be collected in a software, but when you are trying to build an application that will perform machine learning in the background, you can collect all this information into your data set, but you are not using them. You are removing those kind of data because they have no use to you. Because the only type of data useful for you in machine learning are numeric data and categorical data. I explained categorical data in our last class, where I said categorical data are those data that belongs to that groups things into one group or another. For instance, gender, male and female, they are categorical data. Data like class A, class B, class C, they are categorical data. Or yes or no, all these are categorical data. So those type of data they are important also when you are doing machine learning model development. And we said why are they important? They are important because machine learning allows you to convert this data to numeric data using a simple SKLM preprocessing library called label encoder. I showed us how to make use of the label encoder in our last class. We used it. I'm trying to get there where we used it. Okay, this is where we used the label encoder. We have a data set called good bad size, which was formerly strings. However, it is a category. So we needed to convert it. So to convert it, we used the label encoder where we initialize the label encoder. Mind you, one thing with machine learning is whenever you are trying to use a particular library, you will always initialize before you convert. You always initialize before you convert. So that's one thing with machine learning models. So after initializing the name of the label encoder, because that's what you use, you will specify that column that you want to apply label encoder on. So immediately you specify that column, you write your equal to, then you call the label encoder by the name you give it, which is NE, then dot fit transform. I said this fit transform is very, very important because the fit transform is what allows application of this label encoder on that column within your data set. If you didn't put this dot fit transform, it will never be applied on the data set. So after initializing the model, you have to apply, you call the model and then write this dot fit transform, means I'm giving you authority to convert. That is what this dot fit transform signifies. Then you write the same name of this column you wrote here, you still write it inside your bracket. Then once you run it, you have categories now. And I told you it does this categorical representation based on alphabetic order. So we have good and bad. In letters, B comes before G. So B will be given 0, then G will be given 1, which was what we saw here. You can see those ones that have bad, bad. The first two were bad, bad. You can see 0, 0. Then the third one was good. You can see 1. Let's go back and verify that. You can see we have, okay, sorry. Okay, I think there was something I did here. 156. Okay, yeah, this was the place I picked the data from 156 downward. Bad, bad, good. So you can see it here, 156, 0, 0, 1. That's bad, bad, good. So that's how we do label encoding. So that is that on what we did in our previous class. We did exploration. I showed you different commonly used type of chart, and I explained what these charts mean. And like the box plots, I told you, all these ones represent outliers. It means they are far from the default point. And I told you outliers are points that they look non-realistic. There are points in your data that look non-realistic. For instance, this data is telling us that, because this is a data for shoe size, it's telling us that a person has shoe size 90, which is almost practically impossible for someone to have shoe size 90. So those type of points are what we call outliers. And when you are building machine learning model, you either remove the outlier or you use it with outlier. So in our subsequent class, I'm going to teach you how to, though that's not what we are doing today, but in our subsequent class, because I know maybe time might not permit me today to do practical applications, or even if we'll do it, will be little, I'll have to stop somewhere. So in subsequent class, I'll teach you further data preprocessing, because I said data preprocessing is much. We have different types of data preprocessing, and the better you do your data preprocessing, the more accurate your machine learning model becomes. So the more, or the good analysis you give to your data set during data processing determines how well your model is going to be working. So I said we have different type of data processing. One of it is this label encoding that we did. Another type of preprocessing we did is feature engineering, which I say you can create new features in your data set using the ones that are already existing. Like initially our data set didn't have this shoe size status, it doesn't have this shoe height. If you recall that day, our original data set has just height, gender, and shoe size. Yeah, height, gender, and shoe size, but we're able to create two more features. So those are what we call feature engineering. So all these are processes that you can use to improve, to process your data. All these ones are also data preprocessing, where you ensure that the data sets, the data types of your data are in the right format, dropping missing values. All those things are what we call data preprocessing. So you have to do them to ensure that your data is in the right format to accept a machine learning model. So those were what we looked at in our last class. So what we'll be looking at today is an introduction to machine learning itself. So machine learning, though I've spoken about this in our very first class, so today I'll talk about it in depth, since this is where we commence our machine learning properly. So machine learning is an aspect of technology or is a subset of AI because we have artificial intelligence and we have machine learning. Whereas machine learning is the building block of artificial intelligence. So machine learning is an aspect or a subset of AI that focuses on building machine learning model, whereby you build models. Now, mind you, there's what we call algorithm and there's what we call model. Algorithms are what I use in building model. For instance, random forest algorithm is an algorithm that is already existing online. Me, I will pick it and then build my own machine learning model. So the one that you build is called model, whereas what you use in building it is what we call algorithm. So you might hear me interchanging them at times. So know that whenever I'm talking about model, I'm referring to the one we are building by ourselves. Whereas if I say algorithm, algorithm is the one that is available online. Ours is to go and pick it. For instance, that label encoder is already available in SQL. So that label encoder is an algorithm. It wasn't we that created it. But once we applied it, we that LE equal to label encoder. Now that LE is like a representation of the algorithm. So it's now a model for us to use. So that's the difference between algorithm and models. So machine learning is an aspect of AI that focuses on building models that can predict or make decisions similar to human beings. A practical example is spam detector. Most of the times when they send you an email that is spam will not come to your inbox. It will move to your spam folder. How does it know? It's because AI, these machine learning models were used to build a machine learning algorithm that will tell any email coming into your Gmail. It will tell it, okay, check this email critically. Does this email has features of spam? If it has features of spam, it will tell it where move it to your spam folder. So in in your code for writing for Gmail, in the code used for developing Gmail, there was a function that was created there that whenever the spam detector, that is the machine learning model built to check whether a message is spam or not. Whenever it identifies that this mail has potentials of being spam, it should move it to the spam folder. Then they will give it the location of that spam folder. So it's going to move that email directly into the spam folder. Whereas the ones that are not spam, it will be giving link to your primary inbox. Then it's going to move that particular mail to your primary inbox. So spam detection is one of the commonly used application of machine learning model. However, it is a classification task because we have two types of machine learning model, which is what we two types of supervised machine learning model, which will be one of the things we'll be looking at today. So practical applications of machine learning, they involve spam detection, image recognition, whereby a I can just upload your picture to a particular database. Like in American movies, you can see at times they will just snap somebody and then check online, and then the algorithm will detect the name of the person. All those things are what we call image recognition. They are being done using machine learning. House price prediction or price prediction, personalized recommendation like your music app, all this Spotify, e-commerce websites. At times you enter, they will recommend a music for you based on what you have been searching online. All those kind of things are done using machine learning. So that is what machine learning is. It has to do with building machine learning model for performing prediction. Now, we have three classes of machine learning models. However, for this course, it's just the first one we'll be looking at because unsupervised reinforcement, those ones are advanced machine learning classes. They are not meant for this level for now until you become familiar with the lower level machine learning model before you can then transverse to the advanced ones. So we have three types of machine learning model. So please pay attention to their difference. The first one is the supervised learning, the second one is the unsupervised, and then the third one is the reinforcement learning. Now I'll start from the reinforcement learning, then I go up. Now, what are reinforcement learning? Reinforcement learning are machine learning is a type of machine learning class that focuses on, here I wrote trial and error, through reward and penalty. Now, a practical example of reinforcement learning are all these robots that usually mimic human beings. Those are practical examples of machine learning model. For instance, there are some. I think I can't really recall the name, but there's a doll. It looks like a doll. Most of the times, I do see it in maybe for all these children. They are used for children. Maybe when a child is crying, I've watched some content like that. A child will be crying, and then they will use that doll for the child. When the child maybe is crying, the doll will be mimicking the child crying. Now, those type of robots are what we call machine learning robots built using reinforcement learning. In reinforcement learning, the machine learning algorithm will be built to look at you as a human being and then learn from the way you are behaving. That is, he will, like the way I am now already as a person, I will have that machine learning model system built using reinforcement learning with me, and the way I am behaving, it will be mimicking, it will be learning from my immediate behaviors. So that is what we call reinforcement learning. So reinforcement learning, just like I said, okay, I said reinforcement learning are basically a class of machine learning that allows AI or robots to learn from your behaviors. So those what we call reinforcement learning. So just like I said a machine learning system will be built and allowed to mimic you as a person. So that is that. Now, the second class of machine learning models is the unsupervised machine learning model. Now, unsupervised machine learning is a type of machine learning whereby you'll be given a data, whereas the data doesn't have a label. Let me show you a practical illustration of what I mean. For instance, the data set we'll be using, which is the shoe size data set. Okay, like the shoe size data set now, this particular data set, I call it the shoe size data set. Why? Because this particular data set, at the end of the day, like in from today's class or next class, we are going to build a machine learning model that will be predicting people's shoe size. So that's why I call this the shoe size data set. Now, this type of data, whereby what you want to predict is being given to you, that type of data, we call it labeled data. So a data that has what you want to predict in it is called labeled labeled data. So those type of data, labeled data, we usually use them for, we don't use them for unsupervised machine learning. Rather, that those are what we use for supervised learning. If you see, I said in supervised learning, I said models learn from labeled data with explicit input output pairs. That is, in your data set, you have input and you have output. Whereas, I will explain what input and output mean. Whereas in unsupervised learning, we say models detect hidden patterns in an unlabeled data without guidance. So, unsupervised learning, unsupervised learning, let me show you a practical example of unsupervised learning. Now, I've deleted the shoe size column. In an unsupervised learning, I will only give you height and gender, but I will tell you categorize these people, group them based on their shoe size. I want you to work with shoe size, but I didn't tell you I've deleted the shoe size column here. Those type of work is what we call unsupervised learning. That one focuses on grouping people. So it's going to group people. Okay, maybe people that have height 140 to 150, to group them to one group. And then it will say, okay, maybe these people, their shoe size is maybe between 30 to 40, to group them. Okay, these people, their height is from 160 to 170, and their gender mostly is male. It will group them to one side to say, okay, these people usually have shoe size between 40 to 42. Now, that is how unsupervised learning works. You are not going to give him that data that he is going to predict. Rather, you tell him he should group people. And that is what they usually use in recommendation system. That is why it will check your search history, things that you've searched, the musics you've searched online, and then group musics. That is why it doesn't bring one recommendation to you. It brings plenty recommendation to you based on how you've searched. So that your search are like this height and this gender, the default data given to him. Whereas that recommendation it brings to you is that group that it has identified, just like I said, group or shoe size. So that is how unsupervised learning works. So unsupervised learning works by checking, learns from an unlabeled data. And I said, what is an unlabeled data? What is a labeled data? A labeled data is a data that has that thing that you are trying to predict is inside the data set. Whereas unlabeled data is a data that thing you are trying to predict is not in the data set. However, the only thing you can do is for you to group them together based on similar properties. So that is what we call unsupervised learning. Whereas supervised learning, I said learns from labeled data. And I say labeled data is when you have that particular thing you want to predict. Now back to what we call input and output. That particular column you are trying to predict, we call it output column. Output column. We call it output column. Whereas those features, those other data that you use in predicting this column, we call them input column. This one is not important, so let me drop it. So this one, your height and your gender, we call them input columns. So these ones like this, these two, they are input columns, whereas this guy here is your output column. Why is it an output column? It is an output column because that's a column you are trying to predict. Whereas input columns are those columns that you use in predicting your output column. So those are the three types of machine learning. We have what we call supervised learning, we have what we call unsupervised learning, and we have what we call reinforcement learning. I say reinforcement learning is a class of machine learning algorithm whereby a machine learning model learns from a person. That's the reason why it is called try and error. It will be doing some try based on how you are behaving. And if it gets it correct, it is a reward to that machine learning robot that is being built. So that's what we call reinforcement learning. Then the second group is the unsupervised learning. I said unsupervised machine learning algorithms are algorithms that learn from unlabeled data. That is a data that doesn't have what you are trying to predict. That's what we call unlabeled data. Then the last one is the supervised learning. And I said the supervised learning is a class of machine learning algorithm that learns from a labeled data. So this one has a labeled data. That is what you are trying to predict is inside the data set. So it is very easy for you to make use of. So just like I said our class will focus on supervised learning. Now, just like I said, one of the features of supervised learning is training on labeled data. So after you train on labeled data, you will now predict new inputs. In the sense that after you build it to predict a particular output, you give him some data to then predict. That is what we mean by predict new input. For instance, in our data set here, let's say we have used height and gender to build a machine learning model that can predict shoe size. This new input means I will test, maybe I'm going to give him a particular height, I'll give him a particular gender number, and then I'll tell you, okay, predict the shoe size for me. It means it's trying to predict new input. So that is what this statement here means. So an example of use cases of supervised learning. Now, this brings us to the next thing. Supervised learning are classified into two. Just like we said, the entire machine learning types, there are three: supervised, unsupervised, and reinforcement. The supervised itself is classified into two. Unsupervised has its own classification. We have clustering, we have association, like that. Reinforcement has its own. But our focus is on supervised. Supervised is classified into two. So please, you can be writing it down somewhere, since this is more of theories. Now we have two classes of supervised learning. We have classification and we have regression. We are going to look at both of them in our course. So, what is classification? Classification is a type of supervised learning where you are trying to predict the class of something or the category of something. That is what we call classification. As the name implies, class. As the name implies, class. You are trying to predict which category or which class does something belong. For instance, if I should say build a machine learning model that predicts the gender of people in this data set, whether the person is a male or a female, that is classification. That is a practical example of classification. Another practical example of classification is the one I gave you. I say spam detection. It will check, is this mail a spam? If it is a spam, send it to this folder. If this mail is not a spam, send it to your primary inbox. That is a practical example of classification. When you are trying to predict, you are trying to build a model that can predict or that can group something into two different classes, class A or class B. That is what we call classification. We have two types of classification. We have binary classification and we have multi-class classification. Now, when we say binary classification is a classification that belongs to only two classes, either class A or class B. Most of the times, we used to call it 0 and 1 because class A, I will give him 0 if I do label encoding, and then class B, I'm going to give it 1. So those type of classification is what we call binary classification and is the most common types of classification. Although multi-class classification is also common, but it's very rare. Multi-class means when you are trying to build a machine learning model that is predicting more than one class. For instance, you have class A, you have class B, and then you have class C. Now, this is a practical example of multi-class. The moment the class is more than two. But if it is just class A and class B I gave you, or class B and class C, or class A and class C only, that type of prediction is binary classification because you are trying to predict just two classes. However, if the number of classes you are trying to predict are more than two, we call that multi-class classification. So that is what classification is. That is what classification is. So that's the first. Now, the second one is regression. The second group of supervised learning is regression. If you check here, I wrote classification, example, spam detection. I say regression. We have price prediction, shoe size prediction. Now, what is regression analysis? Regression analysis is a type of supervised learning that involves you trying to predict continuous value. I will explain what that means. Now, in most search, if you search online, what is classification? They will tell you classification is a type of supervised learning that involves building model to perform discrete prediction or to predict discrete value. Now, what is discrete value? Discrete value is a value that is static. It is either this or this. That's what we call discrete value. It has a limited class or it belongs to a particular category. Those type of analysis are what we call discrete values. So classification works with discrete values, whereas regression works with continuous value. Now, what are continuous value? Continuous value are values that differ from one person to another. For instance, shoe size. No two people can have the same shoe size, but different people can have different representation of shoe size. The shoe size of a small boy is different from the shoe size of a grown-up person. The shoe size of a grown-up person are different because the shoe size of a male grown-up person might be different from the shoe size of a female grown-up person. So continuous values are values that any person can have his own value differently. It's not A or B. Values that are A or B are what we call discrete and they belong to classification. Whereas regression is the one that every person can have his own values differently, can have his own value to that particular prediction differently. Another example is house price prediction. If you are trying to build a machine learning model that will predict the cost of a house, it might differ because the cost of houses in Kaduna is different from cost of houses in Jos. A house that you might get 150 in Kaduna, you might go to Jos, you get it 350. And you might go to Lagos, they'll be telling you 600 or maybe 1 million. So you can see that type of data, they are continuous. Why? Because they differ, maybe based on location or maybe based on some criteria or based on some features within your data. So if I say criteria, I'm still referring to features within the data. So for continuous value or regression works with continuous value. And what are they? I say continuous values are values that might differ from different people. However, classification, I said it works on discrete value. And I said discrete value are values that belong to either one class or another class. So that is what classification and regression is all about. So before I continue, I want to ask maybe there's any question, if you need any clarity on anything, you can ask a question if there's any before I proceed. Is there anyone with any question? Anyone? Okay. But are we together? I hope my explanations are clear.
Yes, it's very clear, sir.
Okay, sir. All right. Thank you.
Yes.
All right. So I've differentiated between classification and regression. Now, all these are very important so that when we commence, you will understand what they stand for. I shouldn't give you a work or maybe I asked you build a regression model for me and you are doing classification. You are trying to build a classification model. It won't work. So that is why the differentiation is very important. Now, we have different types of algorithm for building machine learning models. There are many, but I just picked the commonly used ones. The first group of algorithm are linear models. Now we have linear models. Now these algorithms I mentioned here, some are used for classification, some are used for regression, and there are some that you can use for both classification and regression. But there are some that are specifically built for regression, while some are specifically built for classification. The first one, linear models. Now, what are linear models algorithms? Now, linear model algorithms is a class of algorithm. As the name implies, these algorithms that perform prediction by drawing a straight line. I don't want to bombard you with too much theories. That's why I skipped some things. But each of them, they have a theory behind them. Now, linear, as the name implies, linear models, before they perform prediction, they will draw a straight line and then check lines that passes through or that are closer to the straight line. It will pick those points as your predictions. But that is, by the way, linear model. Know that linear models are machine learning algorithm that does classification by using lines. They use a straight line, a linear line, just like in mathematics. Whenever I hear a linear graph is a straight line graph. So that is how linear models to work. So we have different types of linear model. We have linear regression model. Now, linear regression model, this first model, this linear regression model, it is used only for regression. You cannot use it for classification. Linear regression model is used for regression only. Now, the logistic linear model, we have linear regression model. That's this first one. Then we have logistic regression model. Now, this logistic is the opposite of linear. This one is used for regression. This one is used for classification. If you want to use a linear model for classification, you can only use this logistic regression. So maybe when we start classification properly and then I'm calling logistic regression and you hear me making reference to linear model, it's because logistic regression is the linear model used for classification. Because almost every model has its regression model and it also every class it has its regression model and it has its classification model. So for linear model, this linear regression is used for regression, this logistic is used for classification. We have elastic regression, we have ridge regression, we have lasso regression. Now all of them They are linear models. However, among them, it is only this logistic that is used for classification. All the other ones are used for regression. When I say regression, I mean analysis that has to do with predicting continuous value. For instance, predicting shoe size, predicting prices of house, building models that can predict the age of a person, maybe based off his. I think I'm going to look for a data set like that one. We can build a model on that. Maybe the data set can use somebody's weight, his height, and then maybe gender. And then from those information, you can predict the possible price of age of that person. You can predict what could be the age of the person without you knowing his actual age. So those type of analysis are what we call regression analysis. So in the linear model, this logistic is the only one that is used for classification. All these other ones I mentioned, they are used for regression analysis. Now the second one is the decision tree model. I hope someone is not raising up his hand. Okay. Okay, the time for our first meeting is almost up. So once it stops, we'll switch to the second meeting. All right. So once the meeting is almost stopping, since I'm not in my Google Colab environment, please someone should notify me. All right. So the second class of algorithms is decision tree model. Now, what are decision tree models? Decision tree models are models that perform prediction. However, we say linear models use straight line. Decision tree, they usually build a tree. Now, those of us coming from computer science background, we have learned graphs and trees, where they will tell you this is the node has a leaf node. They will draw something like a graph that has branches. Now, that is how decision tree performs its prediction. It usually creates a tree that has two branches, and then it will check based on condition A and condition B. If condition A is met, it might say, okay, follow my right branch. If condition B is met, follow my left branch. So that is how decision tree works. Know that decision tree performs its prediction by building a tree. It always build a tree and then group its classification. It will now follow that branches to perform prediction. Now, decision tree has two types. We have decision tree classifier, decision tree regressor. There's a place where I wrote all the algorithm out. I think that's the next slide. We have decision tree classifier, decision tree regressor. So remember I told you there are some algorithms that are used for both classification and regression. A practical example is the decision tree. So it has two inside of it. Decision tree regressor, which as the name implies is used for regression. Then we have decision tree classifier, which as the name implies is used for classification. Then the next group of machine learning algorithms are ensemble learning algorithms. Now you can see there are many. We have random forest, boosting algorithm, light GBN, XGBoost. Now all these are ensemble algorithms, and the commonly used one is the random forest. Now what are ensemble algorithms? Ensemble means to gather. That is what ensemble means in machine learning. Now, what is an ensemble algorithm? An ensemble algorithm is a machine learning algorithm that is formed from combining plenty other algorithm. Maybe it combines two or more of another algorithm. But majority of ensemble learning algorithms are formed from decision tree. Like this one, it got its name random forest from decision tree. When you have a single tree, it's just a tree. But once you have plenty trees, it forms a forest. That is why it's called random forest. So ensemble learning algorithms are algorithms that are obtained by creating plenty decision tree. Now, decision tree, they are usually called weak learners. Now, why are they called weak learner? Weak learner means someone that is slow in learning. That is to say, when you build a machine learning model, it is using decision tree. It is commonly believed that that model will not perform really well because decision tree, his method of learning, its approach towards learning is very weak and low. So it is usually seen as a weak learner. Decision tree is usually seen as a weak learner. So that was what brought about ensemble learning models. So ensemble learning models, they are formed from combining two or more decision trees. So if one decision tree, maybe you build a machine learning model, one decision tree is giving accuracy, maybe, let me give an instance, maybe 3%. Once you formed two decision tree. Your random forest might be giving you 6%. So you see, it's an improvement of what was obtained. So these ensemble learning algorithms, they are obtained from this one. Whereas other algorithms like the boosting algorithm, it is not only decision tree. Even logistic regression, linear regression, you can use them in creating them. It's not only decision tree, but this random forest only accepts decision tree. However, these ones at times they can accept other ones, but most times we always use decision tree for them. We always use decision tree for them. It's only in fewer occasions that we can use maybe linear regression or logistic regression, because linear regression and logistic regression at times they are also seen as weak learners, and they are the first group of machine learning algorithms. So the next one, I'm going to skip these neural networks. That will be the last thing I'll talk about. The next one is naive bias. Now, naive bias also acts similar to this linear regression. It also use a structure. However, linear regression usually use straight line. However, naive bias doesn't use a straight line. It uses a line, but the line at times is curved, unlike that of a linear regression. Then we also have support vector machine. Support vector machine is also another group of machine learning algorithm that uses line also, similar to linear regression, similar to naive bias. However, support vector machine, its own type of line doesn't check for points that pass through a line. It checks for points that are opposite to the line. But all of them, they usually use line. Support vector machine, naive bias, linear models, all of them, they use lines in performing their prediction. So if you check naive bias, I mentioned some. I said that we have Gibson naive bias, Bernoulli naive bias, Bayesian ridge. Now, majority of these naive bias algorithm, majority, we usually use them for regression. They are mostly used for, sorry, this Gibson naive bias, Bernoulli, we mostly use them for classification. This Bayesian ridge is the one that we commonly use for regression. Then we have support vector machine. Just like I explained, it uses points a little bit far from the line. And those points, we call them hyperlinks. They are called hyperlinks or hyperlink. So we also have two types, just like decision tree. We also have two types: support vector classifier, support vector regressor. But in support vector machine, we don't usually write it in full. SVC and SVR. SVC stands for support vector classifier. SVR stands for support vector regressor. I hope the meeting hasn't ended. Okay. Then the last one is k nearest neighbor. Now, k nearest, okay, the second to the last, since I skipped neural networks. Now, k nearest neighbor is a type of machine learning algorithm that performs prediction by checking neighbors closer to him. It will check, okay, anybody that is closer to another person, it will group them. For instance, a person that is my neighbor, I can say we are in the same area. A person that his house is in a different location from mine, he's not my neighbor because he's in a different location far away from me. So that's how k nearest neighbor works. It checks points that are closer to each other, and then it check how they behave, use them in making prediction, and then find the average between them. That average that it gets is what it's going to output as its prediction. So k nearest neighbors usually perform prediction based on neighbors that are close to each other. So that is how the k nearest neighbor works. Then lastly, now the k nearest neighbor too, we have a KNN regressor, KNN classifier. That's how it works. The KNN stands for k nearest neighbor. Then the last group is the neural networks. Now, neural network is among them, is the modern machine learning algorithm developed. Now, neural networks, as the name implies, it usually use neuron in making prediction. And neural networks are built similar way to the human brain. Now, we have main neural networks, and we have another group of neural network called deep neural network. For now, we are not going to look at deep neural network for now, but we'll look at it in this course. We'll look at it much later. Deep neural network, they are advanced neural networks. We have just neural networks, or you call them artificial neural networks. Artificial neural networks are just simple neural networks. Whereas we have what we call deep neural networks. Deep neural networks are advanced neural networks that require heavy machines for you to build them. And usually those are what we use in image classification, image recognition, facial recognition. As I was giving an example earlier, we use deep neural networks for them because these other types of algorithms are not powerful enough to do those kind of things. So we usually use deep neural network. So and it's also a part of this course where we are going to learn image classification, how you can classify something based on its image. So we are going to use those deep neural networks too. So that is what neural networks are. And for artificial neural network, that's a simple neural network that you can use for prediction. There are two types. We have MLP classifier and we have MLP regressor. Now that MLP stands for multi-layer perceptron. Now, what do we mean by multi-layer? When we say something is multi-layer, it means it has more than one layer. A neural network itself has what we call layers. We have the input layer, we have the hidden layer, and we have the output layer. Sorry, I forget to include that in a graph, but let me do a quick search and explain that better using an image. Mm, Okay. Now, just as I was saying, I said neural networks have what we call layers. You can see multi-layer perceptron. Now these are what we call layers. We have the input layers, we have the hidden layers, and we have the output layers, like I said. Now what is the input layer? The input layer is the layer that collects your data, because in order for you to build a machine learning model, you have to send data. Those data are the input data, just like what I said here. I said you have the height and the gender, which you use as your input to predict the output. These two here are the input layer. So if you are trying to build a neural network algorithm, we are going to send those input data to this input layer. So this input data will carry those data, perform manipulation in this hidden layer. You are not in charge of seeing this hidden layer. It's the algorithm that is in charge of seeing that hidden layer. That's where it does the prediction, and then it brings out the output layer. The output layer means it's going to make predictions of your shoe size based on what you have given to him inside. So that is how neural network works. So that is that on the different types of supervised learning algorithms we have. Now, this is where I classified the different algorithms and how you can import them if you are trying to build a machine learning model. If you are trying to build a machine learning model, this is how you can import it. If you are trying to build a linear regression model, you import it. Remember that they told us that machine learning, whenever you're trying to import something, like the sklearn library, I say it's specifically built for model development. And I said for you to import something, just like that day that we imported label encoder, we said sklearn.preprocessing import label encoder. Now these ones, they have their specific libraries too where you import. So if you're trying to import logistic regression, if you are trying to import linear regression, sorry, you say from sklearn dot, they are linear models, so they have a library called linear model. So you say from sklearn dot linear models import linear regression. If it is for ridge regression, from sklearn dot linear model import ridge. Now remember I told you all of them, they are in the same category. That's why you can see linear, 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 linear. However, it is their name that change because they are different algorithms, but all of them, they belong to the linear folder or the linear algorithm class. Then the next one is the decision tree. Remember, I told you some are for classification, some are for regression. That is why here you see I said decision tree regressor. Now for decision tree is in a folder called sklearn.tree. So you import decision tree regressor. Now if you check all of them, I always start with capital letter and then word that is different, I start with another capital letter. So if you are trying to import, you must import it exactly the way we did. Now, how do you know? Maybe if you have forgotten, a distinct word always starts with capital letter. Like linear is different from regression. So linear starts with capital letter. Regression also starts with capital letter. Decision tree regressor has three distinct words. So it starts with decision tree. The decision will start with a capital letter. The tree will start with a capital letter. The regressor will start with a capital letter. The same thing applies to random forest. So as long as the word is different, always capitalize. However, join them together. If not, it will raise an error for you. So all these are the way you can import your regression algorithms. Then what about classification? These are the ones for your classification algorithms. So they are also similar too. You can see them. These are how you can import them. I think I've shared this slide to the group. Okay. Yeah, I've shared the slide to the group. Okay. So as I was saying, these other group of algorithms are used for classification. So I will give you the slide so you can be making reference. Maybe when you are trying to build and you don't know the right class, you can just check from the list. However, the more you use it, the more conversant you will be, and there will be no need to be making reference. You can just upload a machine learning class and use. So the next thing we'll be looking at is importing algorithms or the basic steps involved in building a machine learning algorithm. So, just like I explained in our previous class, I said one important step whenever you're trying to build a machine learning model or you're trying to do data analysis or anything, as long as it's data related, data analysis, data science with your Python, the one of the most important thing you do is you import your library. So you can see here, since we are trying to build a machine learning model, that's why the first step stays scikit-learn library. That is, you have to import your sklearn library, which I've showed you an example, like we did in last class, sklearn.preprocessing import something. As long as you are importing something from sklearn, that is what we call scikit-learn importation. We import. So these first two steps are talking about importing the libraries that you need. And then I gave an example here. Let's assume I'm trying to use a linear model. An example, you can see I said from sklearn.linear model import linear regression. Maybe I'm trying to do a regression analysis and I want to use my linear regression model. So I will import it from that class. Then after importing it to build a machine learning model, just like I told you, I said anything you import is an algorithm. So you need to initialize. A practical example of initialization was what we did in our label encoder. Here, this is what we call algorithm initialization, where you give it a name and then write the name of the algorithm. So every machine learning model you are trying to build, you must initialize it first before you proceed. So that is what initialization stands for. And then additional tools here, I said you have to perform steps like pre-processing, feature selection, and then you evaluate the machine learning model. Now, remember I said pre-processing is one of the most important steps whereby you prepare the data. So whenever you're trying to build a machine learning model, you have to prepare it. After you prepare, you have to separate your features, what you are trying to predict and what you will use in predicting them. That is the input data and the output data. You have to be specific about them. Then lastly, we have what we call evaluation. Evaluation means you will check this model that I built, how well is it working? Your machine learning algorithm will never be complete if you don't evaluate it. Evaluating a machine learning algorithm is very important because the evaluation is what tells you how well is the machine learning model performing. So that is that we are going to look at evaluation techniques next. But these are the basic steps if you want to build your machine learning model. We have already learned step one and two and a bit of step We have already learned the whole of step one and a bit of step two. We've learned a bit of step two. Now, what is step one? Step one are the basic things we've been doing, where you import your libraries, you import the data set, you perform data exploration, maybe through statistical means, which we'll be doing, or you perform visualization. That is what step one is all about. That is what step one is all about. Then step two has to do with performing pre-processing, where you process the data. A practical example of processing the data is converting categorical data to numbers, like we did using label encoder, removing any missing value in your data set using the drop now function we've learned, then maybe creating new features, then maybe removing outliers. All those things are what we call pre-processing. And I told you the pre-processing you do in one work might differ from the other one. However, all of them are pre-processing. But one work might need you to drop missing value. Another work might need you not to, because the data set doesn't have a missing value. So pre-processing differ from one work to another. But the important thing is for you to understand all the concepts. The better you understand the concept, the easier the whole process becomes. Then after pre-processing, there's what we call data splitting. And there's what we call data splitting. Data splitting are done in two phases. We have what we call splitting data into dependent and independent variable. Now, when I said dependent and independent variable is the variable you are trying to predict. It is called dependent variable or output column. Whenever I'm saying something and I make reference to output column, when I say dependent variable, you should know that it is that column we are trying to build a machine learning model to predict. That's what we call the dependent variable. The independent or input variables or features are those ones that you will use in predicting the other person. So whenever you are trying to build a machine learning model, before you build it, you need to separate. You need to create a separation. Sorry. You need to create a separation you need to create a separation. There should be a boundary between your dependent variables and between your independent variables and your dependent variable. So there needs to be a clear separation. So that is what we call data splitting. We have two types of data splitting. The first one is this one I explained. You create a barrier between the independent and the dependent. You create a barrier. So the dependent mostly we call it Y. Whenever we are doing prediction, we usually represent it with letter Y because it's dependent on the other one. Now you can see this is a practical example. Though this might look confusing, but once we start doing it, I will explain to you further what this stands for. This x equal to data.ilog in brackets. Now this is what we call dependent. This is a dependent variable. This x is a dependent variable. Then this y is this x is your independent variables because it has more than one variable. For instance, your height, your gender, all of them they will go to this x. Then this y is your shoe size. That is what you are trying to predict. So whenever you are trying to build a machine learning model, whether the good thing, the joy of machine learning model is whether you are doing classification or regression, the steps are always the same. The only place they differ is the algorithm you use and how you evaluate them. That's the only difference. But every other step are the same. The pre-process, the data conversion, data exploration, importation, all they are the same. And it's just repetition. That is one thing that makes machine learning easy to learn. So, but I said in data splitting, we have two types. The first one is splitting into independent variables and dependent variables. And I said independent variable are the ones we call X. We'll do it once we are doing where we involve the usage of numbers, you see them. While the dependent variable, that is what you are trying to predict, we usually pass it to Y. That is the first. The second data split is for you to split your data into training and testing. Because machine learning algorithm is all about training and testing, whereby you train your machine learning model by giving him data to learn from. After it has learned, you will now test him. Now we have three types of data. We have training, we have testing, we have validation. But most people don't usually use validation. Validation is a type of data whereby I will split my data set into training and testing. And then that training data, I will split it again into two, into training and validation. Now, training data is a data that we use to train the machine learning model so that it can learn. Now, what do I mean by training data? Like this, my whole data set. If you check, this data set has, let's see, how many columns does it has? Okay, you can see it has 163 columns. That's the data. Now, in training data, I can say, okay, from column 50, 150.
Up to half of back.
Okay, you have a question?
Because I'm not able to.
Okay, so data splitting into training and testing. This 150 downward, I can say this data should be for my testing. Whereas from 149 upwards down to this first column here, I'm going to use them for training. Now, in machine learning model, that brings me to another important point. You can see in bracket here, I said training set 80%, testing set 20%. Now, what does that mean? Whenever you're trying to build a machine learning model, give the machine learning model more data to train than to test. So in your entire data set, most at times, we usually give plenty data for the training. Like here, I split the data. I just gave an example. I said you can split 80% for training, 20% of the data for testing. You can use 90% for training, 10% for testing. Or you can use 70% for training, 10% for testing. Avoid usage of things like 60% for training, 40% for testing. Is too much for testing. Why? Because you are giving the data small data to train. The more data you give your machine learning model to train, the better it becomes. The better it becomes. Now, the commonly used partitioning of data is 70-30. That is 70% for training, 30% for testing. But we mostly use 70-30 if your data set is plenty. But in our case, our data set is small. We just have 100 and something. So if I like, I can use 80-20 or I can use 90-10. It's very good because the data set is not really much. So you always feed your machine learning model with more data to train. Now, what is the validation split? In the validation split, after I've grouped my data. Okay, I said from 150 downward is for testing. The validation split, what I will do is this remaining data here, if I want to use it for validation, what I will do is what we call cross validation. Cross validation means like this my data now. Let me assume the whole of this data is 140. Let me show you. Let me do an illustration here. Um, okay, let's assume I've splitted my data 80-20 for training and testing. Okay, let's assume the whole of this data is the 80%. 1, 2, 3, 4. Okay, now let me drop one. Let me drop one column. Okay, now let's assume I split it. The whole of this is the 80% of my data for training purpose, right? I'm supposed to use the whole of it for training. Now, in validation, this is how validation works. Inside that training data, validation will split them. Maybe this one is 20%. This one is 20%. This one is 20%. And then this one is 20%. Now 20 gives us 80%, right? Now in validation or cross validation, like I said, what it will do is that it will split this data into 20, and then now in this work I'm doing 4 validations because I splitted in 2020. Another validation might split data 10, depending on the number of validation you tell it to do because you set the number of validation. So now in this my case, I'm doing 4 validation. So how does this validation work? To break this training data into smaller data and then to perform training and testing inside again. Inside this data, the first validation, it will say, okay, this first 20% will be my testing data. while this remaining 60 will be my training data. That's validation one. It will do, get the performance, and keep. All these things I'm explaining are things that happen behind the scene. You will not see them with your eye. I'll just teach you how to just write the code. Everything will just run at once. You see the output. Whereas, but that is what usually happens in the background. In the second validation, this 20 together with this other 20 will be used for testing. Whereas this middle 20 will be used for training. Then this middle 20 is what we will use for testing. That is validation 2. In validation 3, it will use these two together with this last for training. Then this one will be used for testing. Then in the last validation, this 3 will be used for training. Then this last one will be used for testing. Now that is what we call validation split. So in validation split or in cross validation, what your data will do is that 80% that you gave him to train, it will still break it down and then retrain it again. Now the more he is doing like that, the better he learns, because he's going to do a training in validation 1, it will do a training in validation 2, it will do another training validation 3. It's as if he's doing 4 training. But if you didn't do cross validation, it's going to do only 1 training. So a person that you train him only once a month and a person that you're training him 4 times a month is going to learn better than that person that you're training once a month. So that is the importance of cross validation. So as we progress, we are going to learn how to do cross validation. But for now, as we are starting, we'll just learn one validation, how to just do one training. However, as we progress, we are going to learn how to do cross validation and how it can improve the performance of your model. Because cross validation can help you to stop some issues within your data set. There's an issue we call overfitting, underfitting. So with cross validation, you can avoid issues like that in your machine learning model, and it will help your machine learning model to be better. So that is that about cross validation. So before I proceed again, I'll give a chance. Maybe if there's anyone with a question, if there's any question, I want to know. But if there's no question, I will proceed. I think no one is raising his hand. All right, so let me proceed. We're almost coming to an end for today's class because I plan today for us to just learn the theories. Then in our next class, that's by next week, we'll start building the models practically. So that is that about model data splitting. Now, classification has its own evaluation techniques. Regression has its own evaluation techniques. Now, what are evaluation techniques? Evaluation techniques are things that you use to check how well is your machine learning model performing. How well is your machine learning model performing? Now, for classification, we have what we call accuracy score. Accuracy score is trying to check how correct is the machine learning model predicting. The overall performance of your model is what we call accuracy score. We have what we call precision, we have what we call recall, we have what we call F1 score. Now, all these are evaluation techniques that you use. Now, precision has to do with how well is your machine learning model trying identify something that is actually true as true. Now, what do I mean by that? Let's assume somebody is a boy and then your machine learning model predicted him as a boy. He was actually a boy and then the machine learning model predicted him as a boy. Precision score will check how well is my machine learning model able to correctly classify that person as a boy. It will measure that. That is what precision measures. So the moment your machine learning model interpreted that boy as a girl, precision will signify that in terms of precision, your machine learning model is very poor. Now, at times, accuracy score is because I'm just using one single example, but if you have plenty data set, there are situations whereby your accuracy score might be good, but the precision is bad because maybe the machine learning model is confused in some places. So if the precision is poor, that is, people that are belonging to a particular class is wrongly classifying them to another class, it will identify that your machine learning model has a bad precision because it's not precise in its decision. So precision focuses on your machine learning model correctly classifying something belonging to a particular class as it's been in that class. That is what precision measures. Then recall has to do with checking. Okay, how well is your machine learning model able to classify that something is in class A, and how bad is it classifying that it does not belong to that class? Now, precision focuses only on how well it is classifying, but precision focuses on how well and how bad it is classifying. So it will check the wrong prediction rate and the right precision rate and then join them together. That is what we call recall. The good prediction rate and the bad prediction rate, and then it joins them together. That's recall. But precision, as I said, it only checks for the correct ones. Once you are wrong, anyway, to just classify that you are not predicting very well. Whereas accuracy is the one that checks both the precision, the recall, the F1 score, and everything. Now, what is F1 score? F1 score is the average of your precision and your recall. That's what F1 score is. F1 score checks the average of your precision and your recall. Whereas accuracy score is one that will join all of them and then check how well are they performing. That is what we call accuracy score, precision, recall, and F1 score. Now, what is confusion matrix? Confusion matrix is a matrix that we use in calculating this F1 score, a precision and recall, because it is a matrix that will tell you these are the number of people that your algorithm predicted them correctly. These are the ones that it predicted them wrongly. That is what confusion matrix shows. To show you your correct prediction by your algorithm and the number of wrong predictions by your algorithm. Then we have AUC, sorry, not AIC. We have AUC, RUC, curve, and score. Now, these ones also check accuracy score, that is how well your machine learning model is predicting. However, this AUC, RUC score is usually use a graph to represent the performance. So that's what differentiates it from the other classification algorithm. So all these ones are for classification algorithm. So if you are trying to build a classification model, you go and use a regression evaluation metrics, it will not work. It will raise an error for you. Or when you are trying to do regression, you go and be using classification, it will not work. So precision, recall, F1 score, confusion metrics, AUC score, they are always only for classification. Whereas for regression has its own. We have R square value. R square value is similar to accuracy score. And another thing, sorry, all these accuracy, precision, recall, F1 score, and AUC, RUC score, they have a range from 0 to 1. The closer the value is to 1, the better the algorithm. The closer the value is to 0, the poorer your algorithm. So the middle is always 0.5. 0.5 is like 50%. So a very good prediction should have 0.7 upward. Any prediction that has from 0.6 downward, we usually consider as a bad prediction. Your model is not performing well. A good prediction is 0.7 upward, 0.7 to 0.9, 9 something. If you have a prediction 1.00, there's a problem with your algorithm, because an algorithm can never be 100% correct. Can never be 100% correct. I'm going to tell you why should an algorithm never be 1.00% in our subsequent class, because it's about overfitting and underfitting. I'm going to explain those concepts and then show you that, because until we've done a work that shows something like that, then I'll explain that concept to you. So accuracy score, precision, recall, F1 score, all of them, they have values between 0 and 1. The closer the value is to 1, the better it is. The same thing applies to this R square value. This R square value also is similar to these ones. It has a value from 0 to 1. The closer it is to 1, the better your regression algorithm. Then the other group of regression metrics we have are mean absolute error, mean square error, root mean square error. Now, all these errors, they are very similar. What they do is they calculate the error, that is how wrong is your machine learning model predicting. For instance, if your shoe size is supposed to be 49 and your machine learning model predicted 50, it is wrong by 1. So the error there is 1. So this mean absolute error, mean square error, root mean square error, what they do is they will calculate the error and then divide it. The ratio of the error is what will become the error of that particular algorithm. So for instance, let me say they didn't even divide it. The error of your machine learning algorithm, which is supposed to predict 49, is predicting 50. The error is 1. So in regression analysis, the smaller the error of a machine learning algorithm, the better it is, because every algorithm will have an error. But the smaller the error, the better it is. Okay, let's assume another algorithm. Maybe I built a random forest algorithm. Instead of 49, it predicted 50. Error is 1. Okay, let's say I built another one. Instead of 49, it predicted 52. The error is 2. I built another one. Instead of predicting 49, it predicted 55. The error there is 6. So if you check, one has 2, one has 1, has 1, 6. Now, among these three algorithms, the one that is performing better is that algorithm that has an error 1. Why? Because it has the smallest error. So if you are doing regression and you are trying to use these errors to check how well your machine learning algorithms perform, these ones, they don't have a range from 0 to 1. No, they don't have. But if you are trying to compare different machine learning algorithms, the one that has the smallest error is the one that is performing well. Whereas that ones that have high error is performing bad or is performing poorly. So those are the evaluation techniques for regression. The only one that allows you to check from 0 to 1 is just this R squared. And this R squared, the closer it is to 1, the better the machine learning algorithm. So those are what I have for you today. So today I just introduced all the basic concepts that you need to understand in machine learning. So in our next class is when we will now do the practical implication. We are going to build a machine learning model that can predict the shoe size of a person. To predict the shoe size of a person, all you just need is to know the height of the person. The moment it knows the height of the person, that's all. We know the gender of a person, because you can, before you ask him, you know his gender, except now that we have transgender, so we are confused. So a man can be transformed to a woman. Aside that, the moment you know the gender of a person, you already know the gender of a person. The moment you know his height, you can then use that data to predict the shoe size without you even knowing the shoe size of the person. So that's what we'll do in our next class. So with this, I've come to the end of today's class. So I just made some outline. These were the things we learned: what machine learning algorithm is, what supervised learning are, the way we can import libraries from sklearn, and then how we can evaluate classification and regression algorithms. So we've come to the